Good morning, everyone, and welcome to this introduction webinar to debug and trace with ARM DS-5. My name is Niklas Jonsson. I work as sales engineer at know-how Solutions, and together with me I have Björn Skjernberg, FA, who will do the technical parts. Before we start, I would like to say a few words about know-how. Know-how has been in the market for more than 30 years, and we work in the areas of embedded design and development, software quality and test, and also functional safety and cybersecurity. Within those areas, we offer tools, training, technical support, and to some extent, consultancy services. We work in the Nordic area, Sweden, Finland, Denmark, and Norway, and we have 3 offices: Malmö, which is also the headquarters, Espoo in Finland, and Herlev in Denmark. We're 18 employees and we have a turnover of 5 million euros. At know-how, we work with market-leading suppliers, and I hope you recognize a lot, if not all of them. Today we will focus on ARM, which is in the center of this picture. And the focus of our attention today is ARM DS-5 Development Studio. DS-5 provides a comprehensive support for system-on-chip designs and bring-ups. It's built on Eclipse for intuitive source coding, editing, project management, and version control. It contains ARM Compiler 5, the compiler version 6, the Linaro GCC, which offers you a toolchain for any project. The DS-5 debugger is unprecedented insight into ARM systems from bare metal, Linux, and Android. You can tune your system for energy efficient throughout your project with Streamline Performance Analyzer. ARM Development Studio 5 is available in 3 different flavors. You have the Community Edition, which is for free, and it gives you access to a limited feature set of the Streamline and the DS-5 debugger. We have the Professional version, which supports all ARM processors up to and including ARM version 7. It provides debug and trace capabilities as well as access to ARM compilers. And top of the line is the Ultimate Edition, which supports the very latest ARM processors, such as the ARM V8. It gives you access to ARM compiler version 6 built on Clang. And if you are developing software for projects that need to be certified, let's say for IEC 61508 or ISO 26262, you benefit from using the Ultimate Edition because there is a safety kit containing a pre-certified compiler and a safety kit. If you need to debug your target software running on target, you can connect various debug probes to your DS-5. You have the Streamline, and you also have the ULINK Pro family, which gives you different features. I think I will hand over to Björn, who will give you a short presentation of the debug and trace functionality in ARM DS-5.
Thank you, Niklas. So, just make me presenter, please. Let me just share my screen with you guys. Okay, here we go. So, my name is Björn Skjernberg. I work as FAE here at know-how Solutions. So this is session 1 out of 2, which is called Intro to Debug and Trace with DS-5. So the agenda for today, I will show you my hardware and software setup. So a little bit of what you need to get started with DS-5. I will give you a quick overview of the DS-5 IDE. I will show you how you can make a configuration to connect your target to do debug and trace. And then I will show you what DS-5 can do when it comes to debug and trace. And we will end with a Q&A. On Thursday at the same time, 9 o'clock, I will show you performance measurement on Linux system using Streamline. So basically doing performance measurement using Ethernet communication to see how your system is performing. And with this Streamline, which is a part of the DS-5, there is no need for external hardware debug, but that's on Thursday. So my hardware setup. I'm using a SED board, which is based on the Sync 7000. It has a dual Cortex A9, so it has two Cortex A9 cores. On top of that, a Linux 3.7 is running. To my targets, I have connected my ULINK Pro debugger. So this will be able to perform debug, and I will also be able to read the embedded trace buffer, which is a 4K buffer that resides on the target to collect trace. I have also connections between my target and host, so I have a serial connection in UART where I can communicate with PuTTY, and I also have Ethernet. My software, so I'm using DS-5 of course. So as Nicholas told you, DS-5 is Eclipse based. So you have your source code and your debug configurations in the same workspace. So DS-5 has of course its own debug perspective, which I will show you in a little bit. So because DS-5 is Eclipse based, you have the possibility to add plugins to your environment. So for me, I have not done this yet, but if you want to, this is always possible. So before we go into the demo, just the contact info. So if you have any technical questions, please contact me, or if you have any sales questions, please contact one of my coworkers. So this is DS-5. So I'm right now in the C++ perspective, which I think is familiar for most of you. So I can edit my source code as I would do, and then build as normally, so to speak. So when I'm going to go into the DS-5, I need to go to the DS-5 debug. So this is the DS-5 debug perspective. So let's go ahead and create a debug configuration for our target. So let's go into debug configurations. We go DS-5 debugger, and I will create a new one. Let's call it webinar SEDboard and ULINK Pro, so we know what we are doing. So first of all, we need to tell DS-5 which CPU am I going to debug and trace. So this is the ones that are supported out of the box. So mine is from Xilinx. So I will choose Xilinx 7000 and it's cascaded. I will choose Linux kernel and or device driver debug. And I can choose either to connect only to core 0 or core number 1, or to connect them both, which I would like to do. I'm using the ULINK Pro, so I need to select this. And then I need to make sure that the ULINK Pro is connected to my host. So I will browse for the ULINK Pro. The ULINK Pro will appear and I will select it. I will also go ahead and configure the debug and trace for my target. So if I click edit, so I will use the on-chip trace buffer, the ETB, embedded trace buffer. I'm going to do trace for both the Cortex A9 cores, so core number 0 and core number 1. And I would also like to have cycle accurate trace. I'm not using the ITM, so this will stay disabled. We click apply, OK. Next off, in files. So in files, you can tell DS-5 to tell your debugger to either load a file from your host to a target, or if you would like to use debug symbols from an ELF file, you can do this here. So I would like to use the debug symbols from the VM Linux image, which I have compiled. But since we're doing Linux debug, I can't use this option here because then the load of the symbols will happen too early. So I will go ahead and do this in my debugger configuration instead. So I will copy paste here. I have prepared. So I will interrupt the execution. I will add a symbol file, and then I will continue execution. Also, since I'm doing Linux debug from main is no good, so I need to connect only. Okay, so we apply, and then we click debug. So now we are connecting to the target, and you see here we get some messages up in the commands view. So we see here enabled Linux kernel, which is good. And we have loaded the symbols to our debugger. So let's break execution. So when I click interrupt, I will see where I am at the moment. So if we have a look at the disassembly, you see where the program counter is standing at the moment. If we have a look at the registers, we see that this is the registers for core number 0. And if I click on core number 1, I will get the registers for core number 1. I also get some of the special registers, so I have these as well available. And if I want, I can have a look at the peripherals. So the peripherals for the Xilinx Sync 7000 is supported out of the box. So if they're not supported, you can quite easily add this. So let's go ahead and pick a peripheral. We will add it to the registers view. And if we expand, we will see what this control register is doing. So when I hover over one of the settings, I will get an explanation what this is doing. And because I have the JTAG access, I'm able to alter the value of every peripheral. So now I'm able to alter this value. But for the demo, let's keep it the way it was. So we also have the functions that I have on target. So let me search for a function. So I will search for the function called doFork. So we see here, double click, and then it will appear here. So if I right click on doFork, I can say show in source, and DS-5 will take me to the source code of where this function is. So if I double click here, a breakpoint will be put on the first instruction of doFork. So we will see this in the breakpoint view. So if I continue execution, and I will give a command that causes a process to fork. So let's say PS, the breakpoint will be hit. Okay. So we see now the breakpoint was hit, and we see the call stack for this here. We can have a look at the variables that are within the doFork. So if you see here that this is all of the breakpoints, this is all of the variables I have in doFork. So if I do not wish to see them all, I can click on one of them, right click, and then say send to expression view. And then only this stack size variable will appear in the expression view. And again, since I have the JTAG access, I have the ability to alter every piece of memory. So I can put this to 1, and the variable of stack size will be set to 1. Also, as you see here, we have a variable called child TID pointer. So this is a pointer which has this value, and since it's a pointer, it's pointing at another value. So this is the value that it's pointing at. So if I were to say show in memory for the pointer, I will see the memory of where this point, what it has, but also you can say show dereference memory. So you would like to show the memory of where the pointer is pointing to. So you get the same 858 here as you get up here. As well, you can step with DS-5. So if we can step source line like this, we can step over if you wish to step over source line, and you can step out if you wish to step out of a function. We can also switch to step by instruction. So when I click this, you will see to your right that we are now stepping the instructions instead, like this. So if we have a look again at the memory window and we remove this, we can have a look at where the PC is at the moment. So with the menu I have here, I'm able to import and export memory. So if I need to do some copying of memory, I can do copy from the target to the host. Or if I need to import memory, I can import memory from the host to the target. I have also the possibility to fill the memory. So if I need to do some stack watermark calculations or something like this. So when I'm done with my breakpoint, I can either disable it for now, or I can remove it by deleting it. So let's continue execution. So this is what I had to say regarding debug. So let's go over to the trace. So I will go into my function view. I will search for a function. So we will search for the function called IRQ supervised call. Double click. So let's put a breakpoint, or let's show first in source code. So this is the source code. So when I double click, I will put a breakpoint, and the breakpoint will be hit quite shortly. So let's have a look at the trace. So we see now the trace buffer is used, and all of the 4K that we have available is used. So if we double click, we will get the full view of the trace. So first, what I like to do is zoom in the trace a little bit. So you see when I click in this window, or where I click in this window below, the other two windows will update and show me the according instruction and also the accordingly source code. So I have full view of where I am. Here we see the percentage of how much time was spent in each function. So this is how much time regarding to our trace buffer. So out of the 4K we have, the do division 64 was the most heavily used. If we have a look at our trace records, we see that we have 1,491 records available. So this is due to that I only have 4K of trace buffer on this target. So if I were to use an off-chip trace method, such as the dstream, which has 4 GB of trace memory, I will be able to get, of course, much more trace than I have at the moment. So let's go ahead and create a new trace buffer. So we will clear the trace buffer, and we will go to where we stopped. So usually you are not interested in the full or everything that's happening on your target. So it would be nice to do some kind of trace filtering. So let's do that. So if I right click here, it will say DS-5 breakpoint, and I would like to put a toggle trace start point. Then at the next line, I would like to put a trace stop point. So again, right click, DS-5, toggle trace stop point. So this will now, so if I continue execution, you see that the trace buffer is filling up quite much more slowly than the last time. So if we break, you see that, of course, 100% of the trace records in our trace buffer is spent in IRQ SVC, but that's expected because we start to trace here and then we stop to trace there. In our instruction trace, we see that we have something called cycle counts. So since my trace is cycle accurate, I can use cycle count as a time measurement between the different tracings, so to say, or from where I left stop tracing at line 203, and then when I continue to start tracing in at line 202, 66 million cycles has elapsed. So this can give me an idea of how much time has passed between these two executions. So this is all I had to say regarding debug and trace. So if you have any questions, please feel free to ask them now. Thank you very much.